Okay, so here's a very general kind of problem. Let's imagine we have an object m1 coming in with a velocity v1 initial. m2, let's imagine that m2 is stationary. So initially m2 is not moving. m1 comes in, hits m2, and then they both move off. Not together, but separately with different velocities. So m1 moves off with some final velocity v1 final, and m2 moves off with some velocity v2 final. Now, I want to make the assumption that all of this occurs in one dimension, in the x-axis, along the x-axis. So we're not going to worry about the vector directions here with x hat. Let's just imagine these as all going in the x direction. So we're not going to worry about the vector signs for now. X hat, everything, the momentum is all in the x hat direction. So from conservation of momentum, we know the initial momentum must equal the final momentum. So that m1 v1 initial, that's the momentum of object 1 initially. Object 2 is stationary, so it doesn't have any initial momentum. So m1 v1 initial equals the final momentum, which is m1 v1 final, that's the momentum of object 1, plus m2 v2 final, that's the final momentum of object 2. Now let's assume that this is an elastic and elastic collision, meaning the kinetic energy is also conserved. So what we have is the initial kinetic energy, 1/2 m1 v1 initial squared, so 1/2 mv squared. That's object 1. Kinetic energy of object 2 is 0 because it's initially not moving. So the initial kinetic energy equals the final kinetic energy, which is the kinetic energy of object 1, 1/2 m1 v1 final squared, plus the final kinetic energy of object 2, 1/2 m2 v2 final squared. So we've got these two equations that relate these quantities that we have. Now, how many quantities do we have? Well, we've got m1, m2, v1 initial, v1 final, v2 final. So there are 5 variables that we're talking about. We have 2 equations. So in order to solve these, with two equations we can solve for 2 unknowns, which means we need to know 3 of these unknowns. We have to have values for 3 of these variables if we want to use these equations to solve for the other 2. Let's assume that we know m1 and m2, and we know v1 initial. So we know what's going on to begin with. We can then use these equations to figure out what our final velocities are. Now, I'm not going to go through that derivation. That's a great math problem. If you want to do it, I suggest you do it, but I'm not going to do it right now. I'm just going to give you the result. Okay, so if you solve those equations, this is what you would get. v1 final is equal to this quantity, m1 minus m2, divided by m1 plus m2, that quantity times v1 initial. v2 final would be 2m1 over m1 plus m2, that quantity times v1 initial. Now what I'd like to do is look at these results under certain circumstances that would be kind of interesting to kind of see what would happen in this problem. First, what do we get if m1 equals m2? So in other words, let's imagine these are equal masses. So we have these 2 balls, maybe kind of like this, where one's stationary, one comes in, it hits, what's going to happen? Well, we get something interesting. If m1 equals m2, what is m1 minus m2? Well, it's 0. So in that case, we find that v1 final is 0. What do we get for v2 final? Well, if m1 equals m2, then m1 plus m2 is 2 times m1. And we have 2m1 divided by 2m1, which is 1. We just get v1 final on the right side. We end up with v2 final equal to v1 initial. What does this mean? v1 final is 0, which means m1 ends up stationary, not moving. And v2 final ends up moving at the same speed that m1 had initially. So what does this look like? Well, it looks like you've got these two balls coming in. One strikes this one and stops, and the other one just moves off at exactly the speed that the first one came in with. So M2 is stationary, M1 comes in, stops, and M2 moves off. Very interesting result. If you've ever played a game like pool or something like that, you might have seen something like that if you've ever had balls interact that way. All right, let's try another one. Let's imagine that M1 is greater than M2. So let's imagine that M1 is a bigger ball than M2, for example. What do we end up with? Well, if M1 is bigger than M2, we subtract M2 from M1, we get a smaller value here. We have a bigger value in the denominator. We have a smaller value divided by a bigger value. We get a number less than 1. We're going to end up with V1 final less than V1 initial. So V1 final is less than V1 initial. In other words, what happens to mass 1? It slows down. What about V2 final? Well, if M1 is bigger than M2, then 2 times M1 is going to be bigger than M1 plus M2. This is going to be a number bigger than 1. Which means V2 final is going to be bigger than V1 initial. V2 initial is bigger, V2 final is larger than V1 initial. So what does that mean? Well, that means we have a situation kind of like this, where M1 is bigger than M2, M1 comes in, hits M2 and slows down, but M2 goes off faster. So this one comes in and slows down, and this one goes off faster. M2 goes off faster than M1 came in. Well, that kind of makes sense too. That's an interesting result. Okay, what about the other way around? What if M1 is less than M2? Then what? If M1 is less than M2, M1 minus M2 is negative. And we end up with V1 final being a negative number. So V1 final will be less than 0. It'll be negative. And then, what about V2 final? Well, if M1 is less than M2, 2M1 is going to be less than M1 plus M2. V2 final will be less than V1 initial. So what does that look like? Well, in that case, we have M1 smaller than M2. So what happens? M1 comes in, hits M2, and does what? It ends up with a negative velocity, so it's going to bounce backwards. While M2 moves off slower than V1 initial, so M2 goes off slowly while M1 goes backwards. Well, that also kind of makes sense. So what I wanted to just show here is that even though we might not put in specific numbers, looking at our results can give us some very interesting insights into a particular problem. Knowing what might happen looking at specific cases. What happens if M1 equals M2, or M2 is bigger than M1, or M1 is bigger than M2, things like that. We can look at some results and get some very, very interesting results about the problem. Okay, now I want to think about something else for a few minutes. We know if we've got, say, two objects, M1 and M2, and let's say that M1 is moving at V1 and M2 is moving at V2, we can define the momentum of the first object, P1 is M1 V1. The momentum of the second object, P2, is M2 V2. We can define what we mean by the total momentum. The total momentum is the sum of the individual momenta, P1 plus P2. So that's the total momentum. It's the momentum of the entire system. But does that total momentum equal some kind of total mass times a total velocity or something like that? Well, we certainly know what we might mean by a total mass, the total mass we could certainly think of as the sum of the individual masses, so the total mass might be m1 plus m2. Is there a total velocity? Or is there some object that's moving at some velocity that corresponds to this velocity? As a matter of fact, there is. It's the velocity of the central point of these masses. What do I mean by a central point? Well, it's a point that we call the center of mass. The center of mass. And this velocity is actually the velocity of the center of mass. We will say V sub cm, cm for center of mass. Well, where is this point? What do we mean by the center of mass? What is the center of some system like this? Where is that center? Where is that central point? Well, the position of the center of mass is defined, and we're going to take a look at it. But I would suggest I've written up some extra notes. So on my iCollege site, sorry, this is basically for my class students. I will see if I can't somehow find out some way that I can actually post this. So if you're just watching this on YouTube, that you'll be able to find these notes. I've written up some extra notes that are on my iCollege site for my class students. Please read through those, the extra notes on the center of mass. It'll help you kind of understand what is meant by the equations I'm about to put up. Okay, so please read those. The center of mass will then define by the equations I'll just put up right now. Okay, here we go. Here are the equations. Let's imagine that we've got a mass, m1, and it's located at coordinates x1, y1. So that's where the mass m1 is. Now, it could be moving, and so x1 and y1 might be changing over time, but let's say at some instantaneous time, mass 1 is at a position x1, y1. And let's say we've got a mass 2, m2, and the coordinates of m2 are x2, y2. The position of the center of mass has coordinates x, cm. Now, cm here stands for center of mass, not centimeters. The x coordinate of the center of mass is defined as m1 x1 plus m2 x2 divided by m1 plus m2, the sum of the masses. The y coordinate of the center of mass is given as m1 y1 plus m2 y2 divided by m1 plus m2. Now, like I said, in my extra notes, I kind of explain where these equations come from and why they make sense. So please read those over. But let's stick some numbers in here and see what we get. Okay, here we go. Let's imagine we've got a mass m1 of 3 kilograms. And let's say m1 is at the point 1 meter, 5 meters. So x is 1, y is 5. And then m2 has a mass of 1 kilogram. And m2 is at the point 3 meters, 1 meter. In other words, x is 3 meters, y is 1 meter. So using those equations for the center of mass, what coordinates do we get? Well, the x coordinate for the center of mass will be m1, 3 kilograms, times x1, which is 1 meter, plus m2, which is 1 kilogram, times x2, which is 3 meters, over m1 plus m2, 3 kilograms plus 1 kilogram. Multiply that out, and we get 1.5 meters. The y center of mass will be m1, 3 kilograms, times y1, which is 5 meters, plus m2, 1 kilogram, times y2, 1 meter, over m1 plus m2, again. Multiply that out, and we get 4 meters. So that means the center of mass is at the point 1.5 meters, 4 meters, which would be 1.5, 4 meters, right around there. That's where the center of mass is. Now you'll notice that for just these two masses, the center of mass turns out to be right along a line, trying to draw that straight, right along a line between the two. So the center of mass is right here in between the two masses, And if you measure these or calculate them very carefully, it turns out that this distance is exactly 1/3 of that distance from there to there. In other words, the mass, which is 3 times this one, is 3 times closer to the center of mass than this one. It turns out, and we'll talk more about this later on, that the center of mass we can think of like a balance point. That if we had these two masses, let's say the 3 kilogram and the 1 kilogram, and we wanted to balance these two masses, it turns out they would balance right at the point corresponding to the center of mass. If we could somehow put them on a balance, that's where the two of them would balance and stay level. So the center of mass corresponds to the balance point. Now, with more than two masses, we could figure out the center of mass. We would just have plus, say if we had M3, M4, we'd have M3x3 plus M4x4 plus M5x5, etc., etc. And then in the denominator, we'd have plus M3 plus M4 plus M5. And the same thing for Y, M3y3 plus M4y4, etc., etc. Okay, so there are some homework problems talking about the center of mass. Make sure to do those. And we'll see the center of mass more later on when we start talking about torques. Okay, very, very good. That's all for now. I'll see you next time.